Hello and welcome. In this video, we will explore the fundamental concepts of integration, a cornerstone of calculus. By the end of this session, you will be able to, first, understand the concept of antidifferentiation as the reverse of differentiation. Second, state and apply the fundamental theorem of calculus to evaluate definite integrals. And third, use the properties of definite integrals to solve problems. These skills are essential for the IB mathematics analysis and approaches higher-level curriculum. Let's begin with the idea of antidifferentiation. This is the reverse process of differentiation. In other words, if we are given the derivative of a function, say d(i)e, our goal is to find the original function, y. Consider a simple example. Suppose we know that the derivative of a function is x squared, so dx equals x squared. From our knowledge of differentiation, we know that when we differentiate a power function, the exponent decreases by 1. Therefore, the original function y must have involved x cubed. Let's try y equals x cubed. Differentiating this gives us 3x squared. This is not quite x squared. To get rid of the 3, we can multiply our original guess by 1/3. So, if y equals 1/3 x cubed, then d by x is 1/3 times 3x squared, which simplifies to x squared. This is the correct result. However, there's a crucial point. What if the original function was y equals 1/3 x cubed plus 2? Its derivative is still x squared. The same is true for y equals 1/3 x cubed minus 7. In fact, any function of the form y equals 1/3 x cubed plus c, where c is an arbitrary constant, will have a derivative of x squared. This is because the derivative of any constant is 0. This constant c is called the constant of integration. When we find an antiderivative, we must always include this constant. We say that f of x is an antiderivative of f of x if the derivative of f of x is f of x. The simplest antiderivative is the one where the constant of integration is 0. Let's work through some examples to solidify this concept. We'll find the antiderivative of a few common functions. First, let's find the antiderivative of x cubed. We know that differentiating x to the power of 4 gives 4x cubed. To get x cubed, we need to divide by 4. So, the derivative of 1/4 x to the power of 4 is x cubed. Therefore, the antiderivative of x cubed is 1/4 x to the power of 4 plus our constant of integration, c. Next, let's find the antiderivative of e to the power of 2x. Recall that the derivative of e to the power of kx is k times e to the power of kx. So the derivative of e to the power of 2x is 2 times e to the power of 2x. To get e to the power of 2x, we must have started with 1/2 e to the power of 2x. So its antiderivative is 1/2 e to the power of 2x plus c. Finally, let's find the antiderivative of 1 over the square root of x. First, it's helpful to rewrite this using a negative fractional exponent. 1 over the square root of x is the same as x to the power of negative 1/2. Now, we need a function whose derivative is x to the power of negative 1/2. The exponent must have been 1 higher, so it was positive 1/2. The derivative of x to the power of 1/2 is 1/2 x to the power of negative 1/2. To get just x to the power of negative 1/2, we need to multiply by 2. So, the antiderivative of 1 over the square root of x is 2 times x to the power of 1/2, which is 2 times the square root of x plus c. These examples lead us to some general rules for finding antiderivatives. For power functions, the antiderivative of x to the power of n is x to the power of n plus 1 divided by n plus 1 plus c. This rule works for any real number n, except for n equals negative 1. The case n equals negative 1 is special. The antiderivative of 1 over x is the natural logarithm of the absolute value of x. So, the antiderivative of 1 over x is the natural logarithm of the absolute value of x plus c. For exponential functions, the antiderivative of e to the power of kx is 1 over k times e to the power of kx plus c. For trigonometric functions, the antiderivative of cosine of x is sine of x plus c, and the antiderivative of sine of x is negative cosine of x plus c. These are the fundamental rules you'll use to find antiderivatives. Remember, the process is always the reverse of differentiation. Now, let's connect this idea of antidifferentiation to the concept of area under a curve. This connection is the essence of the fundamental theorem of calculus. The fundamental theorem of calculus provides a powerful link between differentiation and integration. Let's consider a continuous function, f of x, and its antiderivative, f of x. The theorem states that the definite integral of f of x from a to b is equal to f of b minus f of a. This is the core of the theorem. The definite integral, which represents the signed area under the curve, can be calculated by simply evaluating the antiderivative at the upper and lower limits of integration and subtracting. Let's see why this is true. Consider an area function, a of x, which gives the area under the curve y equals f of t from a to x. So a of x is the integral from a to x of f of t d. Now, let's think about the derivative of this area function, a prime of x. This derivative represents the instantaneous rate of change of the area at x. Imagine a narrow strip of width h at x. The area of this strip is approximately the height of the function at x, which is f of x, times the width h. The change in area is a of x plus h minus a of x. The derivative is the limit of this change in area divided by the change in x as h approaches 0. So, a prime of x is the limit as h approaches 0 of a of x plus h minus a of x all over h. This limit is precisely f of x. This means the derivative of the area function is the original function itself. In other words, the area function a of x is an antiderivative of f of x. Since a of x is an antiderivative, it must be of the form f of x plus c. We also know that a of a is 0 because the area from a to a is 0. Substituting this gives c equals negative f of a. Therefore, a of x equals f of x minus f of a. This proves the fundamental theorem of calculus. Let's apply the fundamental theorem of calculus to calculate some definite integrals. First, let's find the area between the x-axis and the curve y equals x squared from x equals 0 to x equals 1. This area is represented by the definite integral from 0 to 1 of x squared dx. The integral is from 0 to 1 of x squared dx. First, we find the antiderivative of x squared, which is 1/3 x cubed. So we have 1/3 x cubed, evaluated from 0 to 1. Now we apply the theorem f of b minus f of a. This is 1/3 times 1 cubed minus 1/3 times 0 cubed, which equals 1/3. The area is 1/3 square unit. Next, let's find the area between y equals the square root of x and the x-axis from x equals 1 to x equals 9. We write this as the integral from 1 to 9 of x to the power of 1/2 d. The integral is from 1 to 9 of x to the power of 1/2 dx. The antiderivative of x to the power of 1/2 is x to the power of 3/2, divided by 3/2, which is 2/3 x to the power of 3/2. So we evaluate 2/3 x to the power of 3/2 from 1 to 9. Applying the theorem, we get f of 9 minus f of 1. This is 2/3 times 9 to the power of 3/2, minus 2/3 times 1 to the power of 3/2. This simplifies to 2/3 times 7 minus 2/3 times 1, which is 18 minus 2/3, or 17 1/3 square units. The fundamental theorem of calculus also gives rise to several useful properties of definite integrals. Let's review these properties. First, the integral from a to a of f of x dx is 0. This makes sense graphically, as the area of a line segment is 0. Second, the integral from b to a is the negative of the integral from a to b. Reversing the limits of integration changes the sign of the integral. Third, the integral of a sum or difference of functions is the sum or difference of their integrals. This is the linearity property. Fourth, a constant factor can be pulled outside the integral. This is another aspect of linearity. Fifth, the integral from a to c can be split into two parts. The integral from a to b plus the integral from b to c. This is the additivity property. These properties are incredibly useful for simplifying and evaluating more complex integrals. Let's work through a more complex example that combines these ideas. We need to find the area between the x-axis and the curve y equals x cubed minus 3x squared plus 2x from x equals 0 to x equals 2. First, we need to find the roots of the function to see if it crosses the x-axis within our interval. Factoring out x, we get x times x squared minus 3x plus 2. Factoring the quadratic gives x times x minus 1 times x minus 2. The roots are at x equals 0, 1, and 2. This means the function is positive from 0 to 1 and negative from 1 to 2. To find the total area, we must calculate the integral for each section separately and take the absolute value of the negative part. The total area is the integral from 0 to 1, plus the absolute value of the integral from 1 to 2. Let's find the antiderivative of our function. Using the power rule, the antiderivative is 1/4 x to the power of 4 minus x cubed plus x squared. Now, let's evaluate the first integral. The integral from 0 to 1 is f of 1 minus f of 0, which is 1/4. This is the area of the first lobe. Next, the second integral. The integral from 1 to 2 is f of 2 minus f of 1. This gives us negative 1/4. The negative sign indicates the area is below the x-axis. Finally, we add the absolute values to find the total area. The total area is 1/4 plus the absolute value of negative 1/4, which is 1/2 square unit. Let's recap what we've covered. We started with the concept of antidifferentiation, the reverse of differentiation, and learned to find antiderivatives of common functions. We then established the fundamental theorem of calculus, which provides a direct method for calculating definite integrals by evaluating the antiderivative at the limits of integration. Finally, we explored the key properties of definite integrals, which are essential tools for problem solving. You are now equipped to understand and apply these foundational concepts of integration. To deepen your understanding, let's work through some practice questions. Here is your first practice question. Take a moment to read it and try to solve it on your own. Question 1. Find the antiderivative of f of x equals 3x squared minus 4x plus 5. Pause the video here if you need more time. Let's go through the solution. We can find the antiderivative of each term separately. The antiderivative of 3x squared is 3 times x cubed over 3, which is x cubed. The antiderivative of negative 4x is negative 4 times x squared over 2, which is negative 2x squared. The antiderivative of 5 is 5x. Don't forget the constant of integration, c. So the antiderivative is x cubed minus 2x squared plus 5x plus c. Here is your second practice question. Question 2. Evaluate the definite integral from 0 to 2 of 4x cubed minus 6x squared dx. Pause the video and try to solve it. Let's look at the solution. First, we find the antiderivative of the function. The antiderivative of 4x cubed is x to the power of 4. The antiderivative of negative 6 squared is negative 2x cubed. We don't need the constant of integration for definite integrals. Now we apply the fundamental theorem of calculus. We evaluate the antiderivative at the upper limit 2 and subtract its value at the lower limit 0. This gives us 16 minus 16, which is 0. The value of the integral is 0. Here is your third practice question. Question 3. Find the area between the curve y equals sine of x and the x-axis from x equals 0 to x equals pi. Pause the video and try to solve it. Let's go through the solution. The sine function is positive on the interval from 0 to pi, so we can find the area with a single integral. The area is the integral from 0 to pi of sine of x dx. The antiderivative of sine of x is negative cosine of x, so we evaluate negative cosine of x from 0 to pi. Applying the theorem, we get f of pi minus f of 0. This is negative cosine of pi minus negative cosine of 0. Cosine of pi is negative 1, and cosine of 0 is 1. So we have negative negative 1 minus negative 1, which is 1 plus 1, or 2. The area is 2 square units. Here is your fourth practice question. Question 4. Evaluate the integral from 1 to 2 of 1 over x dx. Pause the video and try to solve it. Let's look at the solution. This is the special case of the power rule where n equals negative 1. The antiderivative of 1 over x is the natural logarithm of the absolute value of x. Now we apply the fundamental theorem of calculus. We evaluate the antiderivative at the upper limit 2 and subtract its value at the lower limit 1. This gives us the natural logarithm of 2 minus the natural logarithm of 1. Since the natural logarithm of 1 is 0, the result is the natural logarithm of 2. Here is your fifth and final practice question. Question 5. Given that the integral from 0 to 3 of f of x dx is 5, and the integral from 3 to 5 of f of x dx is 2, find the integral from 0 to 5 of f of x dx. Pause the video and try to solve it. This question tests your understanding of the additivity property of definite integrals. The property states that the integral from a to c is the sum of the integral from a to b and the integral from b to c. In our case, a is 0, b is 3, and c is 5. So, the integral from 0 to 5 is the integral from 0 to 3 plus the integral from 3 to 5. Substituting the given values, we get 5 plus 2, which equals 7. The integral from 0 to 5 is 7. That concludes our exploration of the introduction to integration. We have covered the essential concepts of antidifferentiation and the fundamental theorem of calculus, along with its properties. Mastering these topics is crucial for success in IB mathematics analysis and approaches higher level. Keep practicing these techniques, and you'll build a strong foundation for more advanced integration methods. Thank you for watching.